welcome back. It is a Friday fun day, and we do have to cover a little bit of content first in terms of finishing up what we were talking about with regards to procedure call interface in MIPS. We got into some of it on Wednesday, and the truth is, we won't really be digging that much into the weeds of it. The textbook isn't that great at it. I'll cover conceptually a lot of what it's all about, and then we can really look at what the compiler would generate or what existing code bases are doing, and understanding that there's some quasi standards that are being followed, and that's the whole idea of an ABI. But it's not so much, unlike the ISA, such hard and fast rules that you must do it in this exact way. Um, and that results in a lot of ambiguity in terms of examples you would find in terms of our shared understanding here. I'll try to focus on the things that are by and large the case. So for example, where we left off on Wednesday is by and large you do have this concept of an activation record, right? These frames on the stack. And those are there to allow again your function's memory space to not override each other, to play nicely with each other. The exact ordering is not even necessarily something that matters all that much because that frame, this activation record or this procedure frame, is really only relevant to that procedure itself. So this example says, and this is from the textbook example, would say that definitely you have your saved arguments are put on the stack first, then your saved return address, followed by any other saved registers, and then followed by your local function storage, your arrays and other data structures that are local to that function. If you were to change the order of those things, it really wouldn't affect very much. It would just be the code that you would then be emitting would have to be aware of where stuff is located. So since we tend to compile stuff with one compiler, it tends to play the same way. But conceptually, we have this stack data structure. In MIPS, it's growing from those higher addresses back down to those lower addresses, and certain things we have to store on there to make sure that we can have multiple function calls being active at any one given time. One of the big ones is that return address register, right? The jump and link instruction is overriding that return address register. If we go from function call and then into another function call, we would have overwritten that return address register twice. The second time we do it, we can never actually then, if we're not careful, get back to our original PC plus 4 value. We use the stack for that purpose. Likewise, all those local data structures, they have to go somewhere. We can't necessarily put them in one hard-coded address in memory because you could have the same function that's getting called multiple times concurrently, and then the function would be messing up its own data with other calls of that same function. So that's one of the big pictures of we have to store certain things. We have in MIPS it growing from higher addresses back down to lower addresses. And then we have these two general purpose registers that are dedicated just to kind of do the bookkeeping, keeping track of, in the case of MIPS, the SP stack pointer to keep track of the last word of a given frame, and the frame pointer to keep track of the first word of a frame. I had mentioned, and this is very much the case, that you don't actually need a frame pointer. One pointer or the other is sufficient to keep track of your stack as long as you know how large that stack frame was, and the compiler should be aware of how large the stack frame is. This is more of a assembly programmer convenience issue more than anything else. And you can tell GCC or whatever compiler you're using, and there's a command option for it saying, don't emit a frame pointer. Just skip the frame pointer entirely, and your code will still just work. But the other big picture is as we've been using these different named registers throughout the semester, now most of them have some inherent meaning that we can stop using them somewhat arbitrarily. Specifically, the S registers and the T registers. That corresponds to now whether or not it is your code's responsibility or not to restore the value of them not. Do you have to save those register values before you overwrite them or not? And that's sort of a programmer convenience function. There's a number of registers available for you in your function. There's a 10 of them here that allow you to just overwrite them and just not worry about those values. You do what you please with those registers and expect any code that you call, any callee functions to likewise do the same. But then, if that's not enough, you have additional general purpose registers available to you, but those are then dedicated to the callee functions potentially, or the caller functions could be using them. So you have to then keep track of those. Those are referred to as our preserved or our saved registers versus our not preserved or our temporary registers. And some of those we already said had to be preserved. So the return address was the first example of a register that had to be preserved. And then those S registers are also those values that would then have to be preserved. Be a little careful with that term, saved versus not saved. All those registers can potentially be saved. All the ABI is getting to is whose responsibility is it to do the saving if we want to save those registers. So if you're using in your code those S registers and you're overwriting those S registers, and likewise the RA register, which we do overwrite every time we do a jump and link call, it is our code's responsibility, our function that we're writing's responsibility to save those to the stack prior to overwriting them. Then after our function call, we can then pop those values back off the stack versus those temporary registers. That's our arguments, our value, return values, and our just actual temps. We can just overwrite them and assume that any callee function is also going to do the same. So if I have an quote unquote important temporary register in my code, and I want that temp to be used both before and after a procedure call, well, first off, maybe that's what the save registers are for, so I should maybe be using those first. But secondly, I then have to be responsible for pushing and popping those back out of the stack. And yes, it's not just the registers themselves. If we look at that stack frame, and we will get into this, it's not just the data stored in registers that we're trying to preserve from one function call to the next. It is also any other local memory local to that function that we're wanting to preserve on the stack. That's a good question, and the textbook doesn't necessarily draw it out that well. So let me attempt to draw it out a bit better. This is our example from Wednesday. It was using the appropriate coding font that we should use for all of our cases. And let's say starting with, we don't want to necessarily draw all these functions. Starting with function bar and function baz, we can draw what those stack frames would look like. So in function bar, we can't necessarily say what registers are being used here, but we can at least allocate some region of memory um, and say this is bar's frame. It's not that clear all what's in there, but at the very least, we need that return address register pushed on the stack because bar is going to be doing a jump and link, and that's overriding the return address register. So if nothing else, we have to put something on the stack frame for bar to store that return address register. The amount of total bytes in that frame, and we'll do that via just our bookkeeping arithmetic on our stack pointer, is something that the compiler or you as the compiler should be able to determine. I can't look at this very pseudo sloppy code and say for certain how many bytes there are. There's at least 4 bytes on bar's stack frame to store the RA pointer. Generally, it would make sense to me to store just as many bytes as you need on the stack frame. In certain architectures, there's some implications for having things that aren't nice, neat multiples of something. So you'll see examples where no matter what, it's going to allocate 32 bytes and multiples of 32 bytes. For the code that we write, and I do want people not to get too hyper literal about this or stress out about this. If your code is doing some stack bookkeeping in the beginning, if it's pushing the saved registers on the stack, and if it's popping them back off and doing some bookkeeping at the end, it's fine. If you allocated too much frame pointer space, stack pointer space, it's okay. You've wasted a little bit of memory for a very short period of time, and I wouldn't worry too much about it. If you allocate more memory, and remember, allocation isn't some physical magical thing. It's just incrementing a pointer, changing a pointer. If you allocate too much, you haven't really hurt your performance from a number of instructions perspective. You've just incremented a pointer too much, and that's not necessarily that big of a deal. I want us to remember for this example here that we're starting from high addresses and back down. I think that one process memory layout mentioned that a very high address is our start of our stack. So it wouldn't necessarily be at this starting address, but we know that it's growing, to lower addresses. So it's growing in that direction in memory. So we have our stack frame associated with bar, and then at some point bar is calling function baz right here, and baz we know would have to have some stuff on its own stack frame as well. Try that again. Because baz is going to need a little bit more stack frame than what bar would have here. Yeah, we don't have all the details of what's happening in that code, but we do know that at the very least, if my power goes out here at home, I'm just going to keep trucking through and just assume that everyone can handle this. There's a big storm coming in right now. Um, we do know it's going to have at least its return address to get back to the callee function for it. And in this case for Baz, going back here, we also can see that it does have some local data storage here. In this case, int a of 100. We had some good discussions on Discord last night about the right size of data types and all that, and that's good. In this case, we're assuming that it's a block of memory, and it's going to be put on the frame. Again, it's not a physical copy operation, right? It's it's just allocating space. And in this case, there would be subtracting a value. I'm not in Ames. I'm in Des Moines, so the storm's coming down here. It's subtracting 400 bytes from the stack pointer to have space available for that call to, or for that references to the 100 elements in our int a array here. So the stack frames are going to look something like that for that case. Otherwise, though, the examples you'll see will have quite a bit of variety in terms of how they're actually dealing with the stack. This is a textbook example, and this is where I start to get cranky. I've replicated it directly from the textbook example. It's not so different from the example that was on the screen just a moment ago. Function foo calls function bar. Function bar is what we refer to as a leaf function or a leaf procedure. Because it isn't calling anything else itself, we probably don't have to do as much stack for that. You still can. It wouldn't be wrong if you had a stack frame for that function, but because it isn't calling anything else, it tends not to have to do as much. It's directly just returning as a function of the input and not having to store anything or call any other function. So in this example here, what I think can be confusing if you look at the textbook is it is storing two of the preserved registers here. So because the code is going to be updating the frame pointer, and because it is going to be always updating the RA, because it's going to be calling a jump and link here, we're storing those 8 bytes onto the stack. Couple things, and again, I'll blame the textbook authors. This is their example. Couple things that are a little confusing, I think, about this textbook example are it's allocating more space than what's needed. So it's allocating 32 bytes. Although if this code was instead refactored to say add I sp -8, it would be equally correct. You would just have to update these constant offsets as well. It's allocating more than it needs. Okay, fine. We've allocated 32 bytes. We didn't need it. Still going to work correctly. We'll just have a larger stack frame that's needed. And the other thing it's doing here that I would say is not that typical is that it's pushing the frame pointer on the stack, which is correct from a preserved register semantics perspective, and it is updating the frame pointer to now be the other side of that stack, that first entry in the stack. But then it doesn't use the frame pointer at all in this code. So you could have generated a version of this code that only pushes the return address register on the stack, doesn't do anything at all with the frame pointer, and it would be equally correct. And don't let anyone tell you otherwise. Um, but the basic concept is the same. In the beginning of your functions, you're going to have some bookkeeping with changing your pointers for the stack pointer. That's allocating that much space on our stack, 32 bytes in that example. If it were this example, we'd be allocating at least 104 bytes, right, for that example for the Baz's frame there. Otherwise, the code looks very much the same. And then we would be storing whatever things we feel we need to store on the stack in terms of saved registers. This is a pretty common pattern where it's update stack pointer, push RA on the stack. You don't technically need to save things on the stack until you're updating them. So if this push onto the stack was instead put down here, just in front of the jump and link instruction, it would be equally correct. Because you don't always call a function, right? In the examples we've been talking about so far, we're always calling the callee function. But if that was inside an if statement, where sometimes you call function bar here and sometimes you don't, it would potentially make sense to only be pushing things on the stack once you actually know that that function call is going to happen. Either way is correct. It's just two different ways of thinking about the same way of doing the bookkeeping with regards to this. And again, the frame pointer and the stack pointer are two different things. The frame pointer is pointing to the first element in the stack frame, and the stack pointer is technically pointing to the last element in the stack frame. And you can use either of them or both of them in your code. The argument, at least the textbook argument, and why historically we have had two separate ways of keeping track of our stack frames, is that the stack pointer can grow and shrink dynamically throughout your function's execution. A lot of potentially conditional function calls inside your own function. Your stack's going to be conditionally growing and shrinking over time. So that code that does loads and stores only relative to the stack pointer might just get messy. I didn't say impossible. It's still very possible to do it. But just keeping track of where your stuff is relative to this stack pointer that could be growing and shrinking over time, it requires a little bit of thought. That's all. You have to keep track of, well, because I called this function here, I allocated 32 more bytes on the stack. So all of my references to my local structures now need to be, if I use them in between that, an extra 32 bytes away and all that. Whereas the frame pointer won't change inside your function because it's growing back and shrinking in this direction. The frame pointer itself is not changing. So your code arguably looks a little bit cleaner. Um, that's why it's somewhat of a redundant register for that purpose. If you're writing assembly, it could be useful. If you're a compiler that's very capable of keeping track of where pointers need to go, it gets that basic math right usually. You don't need a frame pointer. And that's why I mentioned you can tell the compiler, hey, ignore or just don't even try to generate a frame pointer for this code. So we have our registers in that example. The textbook also talks about recursive examples. The only reason I bring it up here is, well, recursion is a thing, right? And we have to be able to support it in our procedure call interfaces. I would argue that when you're dealing with recursion, you can't cheat the stack anymore, right? You have to be a lot more careful with how you're doing your stack management. If it's just a one-off leaf function that you're working on for a homework assignment, um, and you do it wrong, quote unquote wrong, I'll say, right? Um, your code may still work and it may just be okay. But when you have a recursive call where it's function calling itself, and if there's any local storage inside that function call, you do have to make sure all your pointer bookkeeping is correct for these examples to work. And that's what the textbook is showing here. Otherwise, there's really nothing magical to it. When we were we to visualize the stack frame for a recursive call, it's still just multiple frames. The only thing that's different is the frame is corresponding to the same function, so they should wind up looking extremely similar. It'll wind up being multiple copies of the same exact return address, for example, because as it's a recursive call, when the recursion starts to unwind and our stack frames start to peel off, it's going to be multiple functions ending and returning back to roughly the same place that they were in the code previously. But we have to keep track of the local state, right? In this case, for calculating a n factorial function recursively, we do have to really keep track of that argument register. Otherwise, we're in big trouble, right? We won't be able to return back the result of n minus 1 times n if we've overwritten n and not restored it from the stack. And that's what this code is doing here in this example. It's keeping track of n so that we can call this function n times recursively and have that value back and just multiply it back to get the end result. And then the textbook also does talk about, tail recursion and how you can actually um, modify your code or refactor your code so that it's not actually using recursion at all. That really doesn't have anything to do with MIPS or with microarchitecture. That's always the case that you can do that, but there's nothing 381 specific about that. That's just reminding, I guess, you that just because something's written recursively doesn't mean it has to be a recursive function. There's usually more than one way to implement a specific algorithm we may want to have. But I wouldn't worry about that all too much either. And then finally, the last thing I kind of threw in at the very end of this lecture, but it really should have just been a standalone thing. We've already had a couple of homework assignments that are touching on this concept, and I made a video too, but whether or not anyone watches those, um, this concept of pseudo instructions and what it means to be a pseudo instruction versus a quote unquote native instruction. So context switch for us here. This is us kind of moving into just a little one-off topic separate from anything with regards to stacks here. This concept of pseudo instructions are additional functionality that it's nice as an assembly programmer to have, allow you to do maybe more powerful things, more expressive things in your assembly, but that the instructions you're writing don't directly correspond to native assembly instructions in MIPS. So this is a decent example to start with. This is your move instruction. Move is what I would call a pseudo instruction, right? It doesn't exist in terms of your MIPS green card. It doesn't have an opcode. That would be another way to describe whether or not something is a pseudo instruction or a native instruction. There is no opcode for move. But having said that, as a programmer, moving or copying is a very common thing we would want to do. In this case, the reason it's a pseudo instruction is relatively straightforward in terms of defending that decision. We don't need an opcode for a move operation because there's many ways we can do it, but we could always implement a move operation via just adding that value to 0 and storing it as a result. That's why we call that a pseudo instruction. In terms of you're writing code for homeworks or exams or anything like that, pseudo instructions are fair game. There's only so many of them. There's not like there's hundreds and hundreds of them. Unless the question specifically asks, don't use pseudo instructions. They're fair game for you to use. What tends to be a very common homework and quiz and exam type question is, how would we implement this pseudo instruction using native MIPS instructions? That's not meant to be a tricky type question. It just tends to be easier to, as opposed to going from C to MIPS, it's kind of a translation question from MIPS to MIPS. And so it tends to be an easier version than the C to MIPS type questions. If we wanted to implement a branch less than instruction, which is not a native instruction in MIPS because it doesn't have an opcode, how would we do that? And we did already talk about that. We didn't refer to this as a pseudo instruction at the time, but in fact, in Mars, as you edit your .s file, you can input this instruction, and when you look at what Mars generates for it, it'll actually generate the two instruction sequence to give you exactly that same functionality. And it's kind of cool. If you're not aware that you're using pseudo instructions, doing that one-to-one comparison between your .s file and the resulting machine code can be a little tricky, but it tends to be simple expansions like from one instruction becomes two instructions. There's a lot that are pretty useful. What the MIPS 32-bit ABI also then says about these pseudo instructions is that the assembler can and should use one of those 32 general purpose registers if it's needed to store a temporary value as part of a pseudo instruction expansion. So that's the last of our 32 registers. We've talked about, I think we've talked about 30 of the 32 registers otherwise. There's nothing architecturally that's enforcing this. This is again just, well, if you're writing assembly code and you're going to connect it to other assembly code that other people wrote, you should be a little careful about your use of the AT register because in fact it could wind up getting obliterated by the assembler itself as it's generating instructions to map from pseudo instructions down to native instructions. And there's a number of examples, and maybe you're already using them and you didn't realize it. The best way to know for certain is to look it up. Does it show up in the green card? Does it have an opcode? We've covered the majority of the integer instructions, so if it doesn't smell right, maybe it's a pseudo instruction as well. And then to load it into Mars is the other way to determine whether something is a pseudo instruction or a native instruction there. Does it get mapped directly? Or does it in fact get translated to another instruction or sequence of instructions that does the same exact thing? Before we kind of transition back a little bit, I just want to make sure we didn't forget about this. Do we have any questions about this? I think it's important that we are potentially using these pseudo instructions, but that's a kind of question you'll see a lot on homeworks and quizzes and the like. We don't have the type of question would be something like, we don't have a move instruction, how would you implement it? And this isn't the only answer, obviously. There's many ways I think you can imagine of getting equivalent of a copy one register to another via adding or subtracting or XORing or doing all sorts of things to be able to get the original value copied over to that destination register. Questions about that? And that's okay if there's not. I think the main takeaway from this procedure call topic is those big picture points, and let me just reiterate that one more time. So, stack pointer and optionally the frame pointer with arithmetic on those to allocate and deallocate memory associated with a function's call. How much memory is something we can determine based on how much stuff we need to keep track of for that function's call. If it's just the RA register, we only need to have 4 bytes. If it's the RA register and 100 ints, we may need to have 404 bytes. So the beginning of a lot of your function calls is going to be add I of the stack pointer a negative value because we're pushing this and it's growing backwards in memory. And then some stores of stuff as needed on the stack. So add I of a negative value to stack pointer, store words of values onto the stack. And then our accesses to things like those registers as well as any local data storage is going to be relative to that stack pointer. So a lot of loads and whatnot and stores relative to that stack pointer inside the function itself for accessing A of I and A of 17 times 3I and things like that. The stack pointer is going to be our starting address for a lot of that accesses, if it's local data. And then finally, at the end of the function, when we are ready to return, we know eventually there's a jump register call. That jump register to RA has to have this stored value in the RA register, so we'll be popping stuff back off the stack. And that would be eventually an add immediate of usually the same exact amount that we allocated in the first place. So if we added immediate negative 404 to begin this function, we would add immediate of 404 to the stack pointer to end that function. And then as we are popping things off the stack, we're then doing loads into the registers that we're wanting to preserve, to restore those values back into the registers. Popping this local storage usually isn't necessary. We can just update the pointers accordingly, right? This doesn't need to go anywhere. We're not putting this anywhere. It was local to that function. Once the function's gone, it's gone, and that memory is just kind of sitting there, but it's not corresponding to that function anymore. This register, though, we do need to restore. For our code to work properly, for that jump register to work properly, we need to quote-unquote pop that off the stack. And again, MIPS doesn't have pop as a native instruction, right? I would imagine it'd be a useful pseudo instruction. But for the pop operation, it's load a value off the top of the stack, update our stack pointer accordingly. Okay, not sensing any questions. Let's talk about this example a little bit more and some of the potential considerations associated with it. So going back to what our code looks like here, where we have just these two functions right now. Function bar is doing whatever it's doing. It's calling function baz. Function baz is doing something. There's another function we can ignore for now. It has some local data storage associated with it. And we see baz's frames here has not only whatever preserved registers we need to have, it also has that local data storage corresponding to that array. But there's a funny thing that happens here in terms of how MIPS and many architectures are dealing with these stacks and how they grow relative to local data storage. I'm going to do my best to draw as best I can here, is that we have these stacks that as we push this frame on, and yes, push would also be a great native instruction or pseudo instruction for the same exact reason. As we have these stacks that are growing backwards in memory, we also have these arrays potentially, right, as our local data storage. And I can't draw all of it out here, but if we were to expand upon A of 100, A of 100 is not itself growing or incrementing backwards in memory, right? A of 0 would be over here, followed by A of 1 growing upwards in memory, right? Usually, at least in C, our arrays are growing sequentially in positive addresses in memory, right? That's how we've been doing our array arithmetic earlier in the semester, followed by eventually A of 99. And a couple people were getting to this question or dancing around a little bit for the homework that was due today that I know everybody submitted and nobody's going to ask me for extensions or anything, with regard to that string comp function, right? And a couple of the questions I was seeing, which were good questions, were, first off, how does string comp or string copy or any of that general class of instructions, how do they know when to be done? And the answer is in the spec, in that link that was provided for that last homework question, which is they stop when they reach a 0, when they reach a null byte. When they're copying these character arrays back and forth and they get to an element that's a 0, that's, at least in C, how we designate that the string has ended. Well, if it's a string copy function, we're copying one input string to another input string, it's the same idea. We're copying that value and we copy, copy, copy until we've reached that zero element. And so someone asked, and this is our Friday fun day. Let's finally get to it here. What happens if there is no zero? What happens if that string continues? You've probably done it accidentally, right? Just writing code and copying things around and getting seg faults, right? Having incorrect malformed pointers is the cause of almost all of your seg faults you would be getting. In this example, we'd have to refactor the code a little bit, but let's imagine that inside this function somewhere, there is a string copy call. I don't recall which one's destination and which one's source. It doesn't matter. But in the middle there's a copy. We're copying from some other source location into that array. And that's a very natural thing we would want to do in a function, right? We have an array. We are wanting to copy things into that array and then do something with that local copy of the array. And just like the string comp function were looking at, string compare function you were looking at for that homework question, string copy, the code is really similar. As opposed to just checking the equivalency of two strings, it's loading from one string and copying into the other string, loading from one string and copying into the other string, and stopping when it gets to a zero. Not stopping after 100 bytes or 100 elements because this happens to be 100. The string copy function has no idea that this has a value of 100 and only 400 total bytes associated with it. So what does happen? Well, in this case, as we're copying something in, and let's say we're copying a value of b into that array, it would do what it's supposed to be doing. It's relative to the stack pointers, it's copying it over. It would copy b of 99, and then it would keep going. If there's no zero terminating value to tell it to stop copying, it just won't stop copying. So what happens when we write b of 100 or overwrite a of 100? Think of it as either a second array b or the original array a. What happens? Someone's got the right term there, but literally what happens in terms of our stack frame when we write to a of 100? Your code crashes, right? I mean that's what we'll see a lot of these cases. What will happen ultimately? So Stack Overflow is the term. That's correct, but that's not what happens, right? That's a term we use to describe. Yeah, it would overwrite all sorts of stuff. It would overwrite the rest of that stack frame, as well as potentially other stuff that happens to be located there. From our perspective, the one that would really be concerning would be instead of RA being stored here, memory is just memory, right? Just addresses pointing and overriding them with loads and stores instructions. We would override our RA register. Maybe the code would still be working for the most part until it got to the point where it was then time to return back at the end of function baz here, and I don't have the return shown here, but when that return is ready to happen, and we would want to grab RA back from the stack and then do our jump register to RA, we have lost our RA register. We've overwritten it with a 100. That's going to crash, right? Whatever happened to have been copied into A of 100 is going to become our RA register. The operating system, it's going to do some things where it tells us, well, this address for our program counter corresponds to instruction memory that's not owned by this process. That's the common cause of a seg fault, either data access or instruction access out of the pre-approved range for that particular process. It's going to crash, right? It's going to overwrite that. It's going to crash it. That's referred to as a buffer overflow. Otherwise also referred to, and they're very similar complementary topics, buffer overflow or a stack overflow. So that website you go to Google VHDL questions and get the wrong answers, and then I have to sit with you. That's fine. That's where the name is originally coming from. So that's certainly a crash. That's a bad thing happening. But let's think about, put our black hats on at least briefly here and say, well, if I know I am interfacing with a piece of code that is vulnerable in this way, and lots and lots of code bases, historical code bases, modern code bases, everything in between is vulnerable in this way. It's not just the string copy function. If someone waved a magic wand and said no one can ever use string copy ever again, and people have tried basically, there'd still be sort of scenarios that do basically the same thing, just not in an obvious of a package as we have here. But if I know that I'm going to be interfacing with this and I have the opportunity to provide input function or input string B that I know is going to be copied into input array A, and I know that the bounds aren't being checked for all sorts of reasons, whether using an insecure standard library function that's existed for 40 years or just via some bespoke code that's just not keeping track of pointers properly. I have the opportunity not just to overwrite RA with A of 100, but as an attacker now, I can overwrite that with whatever I want. And consequently, we can get the code to crash. That's already going to happen, and as we test it, we're going to crash it quite a bit. When it gets time to have that jump register to RA instruction that is returning back on whatever got popped off the stack right here, I can now direct that code to when function bar returns to not return to the caller function anymore. Not return, it's bad. I'm using the wrong term here. Not return back to function bar, but to return back to whatever, or in this case, wherever I want within some reasons. One common attack that I think it's fair to call this a multi-billion-dollar software vulnerability that has existed for decades. It's mostly resolved today, but it's still an issue we have to be aware of. Is in doing this copy, what I actually do as I'm copying these values of B. Yes, right here, I'm going to overwrite this with my value of RA. And what people have shown quite convincingly, and I posted a link on Discord to sort of the seminal paper that explained that for a layman to be able to follow, is I could actually tell it, actually return back into the stack itself. Set RA to actually correspond to some location in the stack. What's in that location in the stack? Well, it's these values of B. But instructions are just data, right? This is our stored program concept, right? Instructions are just data that the processor recognizes follow a certain pattern to having opcodes in certain places and register fields in other places. So as I'm overriding this B array and I'm copying and I'm overriding the stack frame here via some buffer overflow exploit, I'm overriding the RA register to return back into the stack. And in here, well, I'm putting whatever I want. I mean, now it's fair game. I'm putting whatever instructions I want by just writing the 32-bit equivalents back into my stack frame. We tend to have a relatively small amount of space to be able to do that. That's referred to as shell code, although it doesn't have to correspond to launching a shell necessarily. That type of attack is the paper that I linked. That's referred to as smashing the stack. It's just a stack overflow in which we are overriding it with executable code. Demoing that is a lot harder today than it was in 1996 when that paper was written, but it's actually still doable. Here's a piece of code. Let's try it. Let's not smash the stack, but let's show what happens with a buffer overflow exploit. So this is a very similar piece of code here. People can see this. Okay, thumbs up, at least for William, if you can see this. All right, thank you. I see your picture there. Oh, sideways. Okay, let's make it a little bit larger then. Okay. This is very close to the code that we were just showing there, right? This is function main. I call this blatant cheating to make life easier. I'm just printing out the pointers for these functions here. Call function foo and pass it a user supplied string. Okay. Inside function foo, some more cheating code to make my life easier. Don't do as I say, don't do as I do, but fine. Inside this array, there's same thing. In a local storage, or inside this function, there's local storage that's going to be put on the stack, and then there's a string copy call. This looks like CPRE 185, SE 185 type code that we write all the time, right? So from main, take an input. That's just parsing the command line input, pass it as an input to function foo, string copy from function inside function foo into that local buffer, this value of input, print out the string, and for my debug purposes, because I'm not that great at debugging stacks, just print out pointers that pop off the stack. So I can see so I could see exactly what's happening in memory. Okay, so this is code that's obviously it's not doing anything terribly interesting, to be fair, but at the same time it is not so dissimilar an example from what you would maybe write for other purposes, right? Let's see if I can make this a little bit larger as well. It doesn't like copying commands into that. I guess that makes sense. So I'm compiling it. Compiling with a couple flags. If we don't run out of time, I can talk about that allow this to actually work in practice. Um, M32 so that we don't have to deal with 64-bit pointers, which just get a little messy and hard to read. But this would work for 64-bit case the same way. So we can run that code, stack smash, and run it with hello. And it does do what it's supposed to do, right? It's printing out a hard-coded address in memory for those two functions. By the way, this was supposed to be the point of it, and I don't know if I really showed it in enough detail. There's this function bar that never gets called, right? There's nowhere here that's saying call function bar and execute function bar. If we see this, we're in trouble, right? Something very bad happened if we ever see this as our code is executing here. So it's printing out some stack values, including one of which should be corresponding to our return. This one should be corresponding to it's not MIPS, right? This is Intel now, so it's ugly and weird, but should be corresponding to our return address for it. We copy hello over, everything looks happy, things are working. Likewise, we should be able to crash this, seg fault this without too much difficulty. We can pass it just a lot of inputs. Anything more than 10 inputs should probably break it. Forgot my alphabet. I assume this will crash. Seg fault. It did copy all that stuff over. The printf function wasn't aware there was an issue. When it came time to return back, we did get a seg fault. So it did overwrite. It was a buffer overflow. We've done that accidentally a million times in our code base here. Let's see if we can trace exactly why it's happening. So I'm just loading it up into a debugger. So over the command line debugging here, just to determine exactly what is happening when we're copying that over. There's a lot of things we could potentially inspect. We can look at the assembly call and actually see. Again, this is Intel. This is ugly stuff that we don't want to worry about. But we could see it's not that different from what MIPS is doing, right? At least at the very end, there's function calls, there's pushing stuff, and then there's popping stuff back off on the stack. So it's not that different than what we are already doing. And we should be able to run it with that same input. And I'm doing multiple letters here so that hopefully I can determine exactly what got overwritten into the equivalent of the return address field in our stack. There's no return address register in 32-bit Intel code, but whatever the equivalent location is still being pushed onto a stack. And that's good stuff, right? So it crashed, which we expected it to for the same exact reason. It sure does. Take a look at that. But not only did it crash, the cool thing is it told us exactly where it crashed. And again, this is Intel assembly. This is on my Windows laptop here. I guess it's kind of a mess. Windows laptop running Windows subsystem for Linux, which is an Ubuntu VM, whatever. But it's a Intel processor underneath the hood here. The cool thing about what GDP tells us here is, hey, it crashed. Not only did it crash, it crashed right here at this program counter or this extended instruction pointer location. Anyway, this program counter location. What do we know about this? 5A, 5.9, 5.8, 5.7. It is definitely ASCII, right? We've passed, and that shouldn't surprise us too much. It's definitely ASCII, right? We've passed in a bunch of ASCII characters. We know that, again, similar to this diagram, we're copying those ASCII characters over, and eventually we're overwriting not exactly the return address, but the equivalent of the Intel return address. So we would expect that to be the case. And I did it kind of indiscriminately here, right? Where I just sent in a lot of characters to get it to crash. 4 of those characters wound up being overwritten, overwriting the equivalent of the return address. Someone can just look up quickly and tell us what characters, what is 5A in the ASCII table? What does that correspond to in characters? I need to know that to actually to break this. I mean, I can do it myself. You guys should be able to do it quicker than I can while I'm managing all this stuff here. Okay, what do we got here? Z. Okay, excellent. So as long as I do this same exact string, and instead of passing it WXYZ, which is going to correspond to nonsense instruction space, if I instead pass it anything I want, frankly, although I haven't provided shell code here, so I'm not going to return directly into the stack, but I can return it this function's address, and it should call that function instead. Yes, yes, yes. Quit anyway. So as I run it instead, let's uh, let's think about that. There's a lot of ways we could type that in. Typing in hex characters directly in the command line is sometimes a pain in the butt. Um, what we can do is instead just use our local Perl and print. It would be 22 characters just to pad that space. And then what was that value? It was 37. Because those aren't corresponding to printable characters anymore, so it's going to be hard to type those in directly on the command line. So here I'm just telling it, run my stack smash code, and in running my stack smash code, take it as an input the output of a Perl command that just prints the character A 22 times. It could have been any character there, and thank you. And then you may have noticed the endianness there, so I got to make sure I have it in the right order. And then for instead of WXYZ, pass it the bytes corresponding to the other function's program counter value. It's one of those things that I say, oh, it's going to work wonderfully, and then I actually try it and it's not going to work. But it should work, right? We've overwritten the stack. We have overwritten where that return address is. We know exactly now what values are getting overwritten. And we still segfault, probably for a number of reasons. But now we've actually called that function that nowhere in our actual C code are we telling it to call. And so since we can control that return address directly now because of just this string copy or again an equivalent type vulnerability in our code, we could tell it to go wherever we want. Now the caveat is people have spent a lot of time, effort, and money on trying to kind of resolve that issue. And if we look at our compile flag, this is me telling it, oh, by the way, turn off all those things that actually make this much harder to do in practice. So there's a stack protector that most compilers do by default. If I were to try this same example with the stack protector turned on, it's pretty cool. It actually says, stack smashing detected, terminated. If you're interested, it's something I can make a separate video on. There are a number of different features that make this type of attack harder unless you're dealing with code bases that don't have those enabled for various reasons. In this case, what the compiler is doing is it's actually when it's creating a stack frame for your code, it's actually intentionally adding what's called a canary value onto the stack frame as well. A randomly generated value that's only purpose is to be checked before and after every function call to see if it got overwritten by someone attempting to overwrite the stack. So I obliterated not just the return address, I obliterated the stack canary, and it can detect that. We can work around that, and there's other approaches that don't require obliterating the entirety of the stack. It's a little bit of an arms race of people coming up with exploit techniques, compiler developers, operating system folks coming up with protective approaches. It's not free though, right? Adding that additional logic to our stack and our function calls is going to cost us some performance. But I guess the trade-off for the default case was considered worthwhile for that particular multi-billion-dollar vulnerability that, as we saw, is pretty trivial to exploit even with just a few lines of C code. Let's leave things here for today. On Monday, what we'll be doing is doing something of an exam review. I'll provide some just sample exam questions, there shouldn't be any shocks or surprises on it on next Wednesday, but I'll just kind of summarize what we've been learning and what I think have been the big picture of what we've been doing with some sample questions. I'll break you into teams to kind of try to work on the questions together. I think if you prepare for it, you're going to be just fine, but we'll use Monday's class to do some additional preparation. Otherwise, good luck on continuing Lab 4. I saw a lot of good progress this past week. Enjoy your weekend, and I'll see everyone on Monday.